Okay, we are going to understand congruence in this first example video. Suppose there's a rigid motion that maps one figure to another. Why does that show that the two figures are congruent? So in our little picture over here, we have our pre-image, figure A, B, C, D, E, F. So this figure underwent two transformations. First, it reflected across line L, which is x equals -1, to get this figure. And then we did a translation. We went 2 units to the right and 5 units down, and this is our image. G, H, I, J, K, L. All right, so rigid motions will preserve length and measure. So let's identify the length and the angle measures of these figures. So in figure A, B, C, D, E, F, the lengths of those sides, we can just quickly count. Side AB has a length of 3, and I'm just counting from A to B is 1, 2, 3. Let's see, BC has a length of 1. DE has a length of 2. EF has a length of 2. And FA has a length of 3. The angle measures, if I look at the angles of each vertex, these are all right angles. So all the angles are right angles. All right, then we did a composition of transformations. We took that figure and we applied the transformation. First, there was a reflection across line L, followed by, so remember, that has to be the second transformation, followed by a translation of, we went 2 units to the right and 5 units down. We applied that composition of transformations to figure A, B, C, D, E, F, and our result was G, H, I, J, K, L. So did the composition of rigid motions preserve length and angle measure? So let's take a look at our resulting figure over here and count up to see if we have any of the same information. So I'm going to go in order. GH, if we count, has 1, 2, 3 units. Next is going to be HI, which is 1 unit. IJ has 1 unit. JK has 2 units. KL has 2 units. And LG has 1, 2, 3 units. And I just realized I missed one up here. Did you guys catch it? AB to BC, I missed CD. CD over here from C to D has a length of 1. So and then all the angles of our final image over here are right angles. So we have all right angles. What we notice is that corresponding sides have the same length. AB is 3, GH is 3. BC is 1, HI is 1, CD is 1, IJ is 1, DE is 2, JK is 2, and on and on and on. So because the measures of the corresponding sides and angles remained the same, we preserved the measures of those. These figures are congruent. We just checked that by actually identifying how long each side was. We have right angles. The corresponding sides were all the same length, and we still have our right angles. Okay, so let's put a couple definitions in our notes. We just showed congruence through a composition of rigid motions. So congruence is figures that have the same size and shape are congruent. Two figures are congruent if there is a rigid motion that maps one figure to the other. Because remember, rigid motion preserves length and angle measure. Congruence transformation. So a rigid motion is sometimes called a congruence transformation because it maps a figure to a congruent figure. So what that could look like, just to show with another figure, let's say we have triangle ABC. We reflect it across a line, and our resulting figure is DEF. This is not drawn all that great, but what we'll find is that corresponding parts have preserved their measures. So angle A and angle D are still the same size. Angle B is still the same size as E. Angle C is the same size as F. Side AB is congruent to side DE. That length did not change. CB and FE are still the same. And AC and DF are still the same. We would say these figures are congruent using this notation. We would say triangle ABC is congruent to triangle DEF. And they are congruent because it underwent a rigid transformation, a reflection, and everything, all the lengths and angle measures were preserved.